Okay, it's part 7 of economic growth and sustainable development, substitution between alternative resource inputs. Bit tricky. I've got to go and have a Zoom meeting later, so this might get a bit cut up, but we'll see how it pans out. So, yeah, let me give you some of the background. So, as you all recall, we started off with, actually, maybe I will use this. Yeah. We've started off with a Cobb-Douglas function, didn't we? And in a slightly more general form, we can write it like this. And this fits the aggregate data, the aggregate long-run data, yeah? But it's so sort of bird's eye. It's not really telling us much about what's really going on. So, and unless we really know what's going on, we can't really predict accurately or have any confidence in using this to predict the effects of, for instance, policy or to predict the future. We want to understand more about what's behind this aggregate data. Okay. And one thing we know that in the short run, this is completely wrong. Yeah, we have much less substitutability between these two inputs. So, for instance, it would make more sense to use a CES and make epsilon negative. Yeah. When epsilon's 0, it collapses to this. But it would make more sense to set this up and make epsilon quite large and negative, like -5 or something. That would fit the short run much better. But then how do we match the long run data? So one thing we looked at was allowing AL and AR to change endogenously over time. That was directed technological change. But we found that actually we can build a theoretical model that has the right characteristics, but it turns out when we look at the data, it doesn't work. Okay, there's problems. Another idea is to say there's actually lots of different products. So this is the production function for one product. And then we've got some overall utility function of all the y's. Okay, where this could then represent a vector of yi's, for instance. And then maybe each product has this short run function, but the long run data is because we shift between products over time. But that still leaves us with, if we think about Solo's mechanisms, that's basically 2 of his mechanisms in that paper from '73, which I hope you've had a look at. So what were the mechanisms? So one was effectively, so Solo was saying, imagine that some R is getting scarce. How do we deal with it? Okay. And he said one thing we could do is boost AR. So implicitly, he's thinking that we've got a production function, something like this. There's no math in that paper, so it's all implicit, or a lot of it is implicit. But implicitly, he's assuming we've got some function like this, and we can raise AR. And he argues that the economy, that will happen endogenously. Endogenous growth theory didn't exist then, but he argues that it would happen endogenously, waving his hands around, so to speak. The other one, he says, is that we could shift from yi to yj. We can change our consumption patterns between the goods where yj has a bigger AR than yi. So effectively, yj, you need less R than yi. But what was the third one? Okay, have a think. You could pause the video if What was the third one? The third one was we could switch from Ri to Rj. If Ri, this is different resources. If this one's getting scarce, we could shift to this one. And then he also says, well, maybe the point is then that we're really good at using Ri. ARI is high, but ARJ is maybe low. So if we want to shift to RJ, we're also going to have to raise this. Okay, so seems like this might be important, right? If you think about climate change, we want to shift from coal to gas, and even better, a lot better, from gas to renewables, say. If you imagine that some rare earth metal is running out, which we're using in sort of windmills or whatever, we want to find some other metal to use instead. That could be the solution. Because there's a hell of a lot of resources out there. There's the sunshine pouring in, it's a phenomenal amount of energy. There's the Earth's crust, as I talked about before, I think is a big place. So if we could just learn to substitute between different potential inputs, that would surely solve a lot of problems. So how do we model that? That's what this lecture's about. And initially, what we're going to do is look at a super simple model where we don't focus on ARI and ARJ, or we keep these constant. And we just say, look, can't we just like, if this is a bit like the consumers shifting, it's not that their preferences change, they just shift. Here, couldn't the firms just shift, even if these are staying the same relative to each other? And that's what we're going to look at first. Do we actually need the solo mechanism of this going up to substitute? And that's this simple model with alternative resource inputs. I'm checking if I have to go to my meeting. Okay, so I'm going to pause there and clean the board. Okay, so what's this simple model going to look like? We're now going to go back to Cobb-Douglas between labor and resources. We don't want to add, we kind of have one complication at a time. This is very common in economics. But now, so we still have, if we set up a profit maximization function at this level, we end up with that WR R is alpha Y, yeah? So the overall input R is its share of total revenue is alpha, yeah? We know that. But now we say, what is this R? R is actually a combination of two potential resources. So we've got gamma C, AC, XC. So the epsilon plus gamma D, AD, XD. So the epsilon to the 1 over epsilon. So we've got a CES function of two inputs, XC and XD, with associated productivities, and then we put in these parameters as well. And because we're keeping this super simple, so we say it's not about AC and AD changing relative to each other. So we wipe those and say they're just equal to A, which we can then take outside. We've got A to the epsilon, A to the epsilon. We take it outside, 1 over epsilon. It's just that, yeah, A times that. So that's because this is a simple model. And we also So this is our technology level for R. We wipe this one, we set that equal to 1 as well. Okay. So then we have yt equals blah, blah, blah. We have R equals AT. And then it's a general equilibrium model. We've got what's going on in general equilibrium. We've got labor coming here, Y coming out here, consumption here, inputs are X, or some of what we produce goes to these two sectors, providing the inputs are C and RD. So this would be like XC, XD. That would be the general equilibrium picture, right? I think that should be straightforward. I think I've got that right. Okay, no, not quite. Not quite. So I've used, yeah, X, the X's are the inputs here. No, I don't call them R's, I call them X's. So these quantities must be W. If we're getting XC out here, the quantity here must actually be WCXC, slightly counterintuitively, and that quantity must be WDXD if we're getting out XD here. Okay, that's not super important. I just wanted to show you that. Okay, so what have we got now? We've got pi equals something. So whose pi is that? It's the pi of somebody who seems to be buying these outputs XC and XD and selling the output RT. Yeah. So it's a bit like in the, it's very like in the structural change model. We kind of impute, you could almost think of it, like I said, in the structural change model, as a retailer. They're not really doing anything in this black box. They're just buying in these, packaging them as a resource input R and selling it on to the final good producers who have this. They're only interested in R. A bit like the consumers in the structural change model, they're only interested in big Y or sort of utility. And it's just a convenient way for the math to structure it. Intuitively, you could think of these being sold directly to here. But this way is super nice for setting up the profit maximization, getting the prices. Okay. Okay. When we've done that, then we can say, oh, the profit function is WRT RT. So it's pi for that guy here is, I'm going to drop the t's, so it's WR times R minus the input costs, which is WCXD WDXD. Okay. And I'm not sure, I don't think I've said, but later on we're going to decide that either these quantities are given and the price is endogenous, or the other way around, that the prices are fixed and the quantities are endogenous. So given this, we can say first order condition in this guy is deciding like how much, if we assume the prices are exogenous, how much of XC and XD to buy in. So if we take first order conditions in XC and XD, what we get, remember this is R, it's A and the square brackets. And we've got an XC here, so we've got 1 over epsilon, this whole thing, the 1 minus epsilon over epsilon, which is R to the 1 minus epsilon. Well, it would be R over A, wouldn't it? So let's see. I need to write stuff down. If pi dxc equals 0, therefore 1 over epsilon WR A, then this square bracket thing, that's R over A. That's the R over A, that's the square bracket term to the 1 over epsilon. But now we've got 1 minus epsilon over epsilon. So it's this R over A to the 1 minus epsilon. Then we go inside and we have epsilon gamma C XC. So those cancel out. And we have gamma C XC to the epsilon over XC equals, minus WC, remember it's the first order condition in XC, equals 0. Okay. Probably for most of you, this is still a bit tricky. Okay, but just, this is the answer. If it's still tricky for you, just practice it, work through it, convince yourself that this is right. And then, of course, we can bring this over and bring the XC up, and we have that. And then we have a symmetric expression, WRA, R over A, 1 minus epsilon, gamma D XD, the epsilon equals WD XD. And then when we divide one by the other, what we get WC XC over WD XD equals, and all this stuff cancels out, and we end up with gamma C XC over gamma D XD. So the epsilon. And what is epsilon? I forgot to talk about that. Is epsilon less than 0, 0, or bigger than 0? Ta-da, it's going to be bigger than 0, isn't it? It's between 0 and 1, because the point is that these XC and XD are good substitutes. So that means if this is the factor shares, isn't it? Or the relative, this is relative factor shares. If XC goes up, because epsilon's positive, the factor share of the clean good, or if this is clean and dirty, say, we'll get there later, but the factor share of the inputs XC goes up when the quantity goes up. It's the opposite to what we had with poor substitutes, epsilon negative. The resource that is cheaper per unit takes the larger factor share. And the advantage is bigger the higher the substitutability between the resources. When epsilon, in the limit, epsilon goes to 1, doesn't it? Then we've got perfect substitutes. Can't get any bigger than that. Okay. As a little aside, we can go back to these equations. They're not actually quite the same, are they? R over A. Let me have a look. Oh, wait. Yeah, sorry, I've been way too quick here. Yeah. I've not followed the notes here, really. We can do this in different ways, actually. Having got this far, I might as well do it in the other way here. Because we've got XCs, which are unknown on both sides here, haven't we? Which isn't great. But if we multiply through by XC over XD to the minus epsilon, then we get rid of them here. But on the other hand, we rather like this factor share thing. So why don't we multiply through by WC XC over WD XD to the minus epsilon. Then we end up with WC XC over WD XD to the 1, and then we multiply through by that to the minus epsilon. So we get that here. And then multiplying through by this to the minus epsilon, these disappear and we get divided by WC. So we end up with gamma C over WC over gamma D over WD, the epsilon. So that actually is a final result, assuming that W's are given and the X's are unknown. Now we've got, oh, and then we raise everything to the 1 over 1 minus epsilon, and we end up with that. That is our final result. And again, if epsilon is between 0 and 1, this is positive. So if WC goes down, the price of input C goes down, its share goes up, because we pile into that input. Oh, it got cheaper, we'll have loads more of it. They're good substitutes. Okay. Similar, if gamma C goes up, which is the productivity of the input, we said it's just constant, but if it should go up, again, we'll pile into using that input a lot more, and its share will go up, which is the opposite of what we saw when epsilon was negative. Okay, right. And if we did it a slightly different way, we would end up with these equations that you can now see. This isn't too important, actually. So I'm just going to talk you through this. I'm not going to work through it. Because we have perfect markets, price equals unit cost. So we have WRR is the revenue of this guy, isn't it? And costs are WCXC and WDXD. So we have WRR equals WCXC plus WDXD. I'm getting stressed now because I've got to go to my meeting. So when we use that and then take the two expressions that you can see on your screen and add them together or inside the brackets and simplify, we end up with the expression you've got on the screen. If I flick the slide, that's the same expression now at the top of your screen. We also have the WRR is alpha Y. So we've now got two different expressions for WR. We can put those equal to each other, and we get an expression for R. So what does that tell us? Well, we have R is AL times a load of parameters or givens. Because the WR and WL, WC, WD are given. This is telling me I have to go to my meeting. Stop. But it can wait a couple of minutes, maybe. So R grows at the same rate as Y if these WC and WD are constant, which is what we expect. It all makes sense. Yeah, this is basically, yeah. WR will be constant and R and Y will track each other. And what we're going to do in the next video, because I have to stop this because I got this other Zoom meeting, is we're going to see how this matches the data. And we're going to see this actually does an amazingly good job of matching the data that I've found, at least on where we see different resources substituting for each other over time. So we don't need the DTC kind of stuff to be going on to match the data. Then we're going to see that when we do throw in the DTC stuff, it actually crashes. It doesn't match the data anymore, at least if we put in powerful DTC. Okay, I got to stop there. So that's the end of video number 1. If I can just make it stop. Which I'm struggling with here.